usually decline to use a microphone and just shout. So I may forget and shout with the microphone on. And if I do that, everybody cover your ears at once, and hopefully I'll get the idea. I want to thank the organizers for inviting me, not just because it gave me the opportunity to give the talk, but because it gave me the opportunity to ask all those annoying questions that I've been asking. Now it's your turn. It's your chance to get even. However, you won't actually be getting even because I actually want you to ask questions. OK, so this is what I'm going to be talking about. It's a theory of, well, maybe it's not. Oh, here we go. Hang on. There we go. That works. Yes. So I'm going to be talking about three seemingly totally unrelated topics. And in fact, there's actually more topics I could have listed up here, including exotonic Bose-Einstein condensation. All these things wind up being described by a hydrodynamic theory of something I'll call polar active Smectics. And this audience is mixed enough that probably everybody has at least one word in this title that they don't understand. But don't worry, I'll explain it. I think I understand what all those words mean. OK, this is work that was done in collaboration with Leiming Chen, who's at the China University of Mining and Technology. It doesn't, as far as I know, have anything to do with mining or technology. We have a preprint out on this. We're currently fighting with the editors of PhysRev Letters to get it in there, and I'll keep you posted. Shouldn't hear anything during the talk, though. So this paper is about the polar active Smectic case, which is what I'm going to talk about today. It's based in large part on prior work done by Tapanat Hayapak, Sriram Ramaswamy, and me, and that work actually came out earlier this year. But I'm not going to be talking much about that, although what we do builds a lot on what they do. OK, so what sort of systems are we going to talk about? This is a picture of one example of an active Smectic. This is basmati rice on a table that's being shaken. Up is normal to the plane of the blackboard, and the table's being shaken hard enough that the rice jumps up and down, and it forms this sort of structure, which the liquid crystal people in the audience will all recognize as a Smectic structure. And here, what I've done is just drawn in the Smectic layers. Okay, and you'll notice that a nice illustration for later on in my talk is that this picture. OK, the last time someone switched off a light, they were scolded and told they had to turn it back on for the purposes of the recording.
The film can't see the speaker.
Right.
So the people remote.
But the speaker that was told that looked better than I do. OK, never mind. All right. So, OK, so all right, so here's an active system. It's active because it's being shaken, and it spontaneously forms a layered structure. There are the layers. And it even spontaneously forms, and this is important for what I'm going to talk about later, dislocations in the Smectic layer pattern. Dislocation, for those of you who haven't heard of it, which is probably about 2 people in the audience, is a place where a layer ends, and they have signs because it can end either as it's going up or as it's going down. Okay, and those are going to play a big role in what I'm going to say later. OK, so that's one example of an active Smectic. It's an active system that spontaneously forms layers, and that's what I mean by an active Smectic. A second example occurs in locusts. And brace yourself, this is a rather terrifying picture. First of all, these aren't actually locusts. These are so-called Mormon crickets. And if you can tell the difference between this and a locust, you're a better entomologist than I am. But they're horrific creatures because they're cannibalistic. And here's an example of one Mormon cricket eating another. And if you didn't already have enough reasons to be thankful that Mitt Romney wasn't elected president, here's another one. OK. So anyway, so that's what Mormon crickets do to each other. Unsurprisingly, therefore, when Mormon crickets are moving together collectively in mass, they pay a lot of attention to what the other Mormon crickets are doing, because they don't want to wind up being the guy on the bottom here. OK? So what was discovered by OK, so if you get enough of these guys together, they'll form these swarms. And what was discovered by Pavel Romanchuk, who's the guy who gave me these horrific pictures, by the way, is that if you develop a simple algorithm for Mormon crickets, locusts, trying to move in a way that they avoid being eaten by other Mormon crickets, they can spontaneously form stripe patterns. They can spontaneously layer, and the whole set of layers moves along with the crickets in each layer running away from the ones behind them so that they won't be eaten by them, and in pursuit of the ones in front of them so that they can eat them. And it forms a layered structure, which is a kind of active Smectic. Okay. Final example is chemical waves. If you Google chemical waves, oddly enough, the first thing that comes up has nothing to do with physics, but it has to do with dark wave, gothic, and post-punk rock. That wasn't what I wanted to talk about. What I want to talk about was this. In chemical reaction diffusion systems, you frequently spontaneously get wave patterns, and in many cases, these wave patterns actually move. And That turns out to be a system that, from a symmetry standpoint, is exactly the same as the other two examples I gave, and therefore should be described by the same hydrodynamic model, which is what I'm going to present you. Okay? So another way to describe a polar active smectic is living, moving soap. Okay? So the soap part is the smectic. That just means a layered structure. Living means it's active, and moving means it's polar. Okay? So anything that's polar and active will move in the direction orthogonal to the layers. So these systems all have the same symmetry. So they should all be described by the same hydrodynamic equations. And what I'm going to do today is formulate those equations and tell you what they imply about the behavior of these systems. Okay? There's a little add for hydrodynamics. In the same sense that all fluids are described by the Navier-Stokes equations, all active polar smectics, all, to use the jargon that was introduced earlier, all dry active polar smectics, that is, active polar smectics moving on a substrate so there's no momentum conservation, should be described by the equations I'm going to present here. Okay, so that's what I'm going to be talking about. So I'll start out by very, very briefly reviewing what's a smectic, because again, I think most people in the audience here know more about that than I do. Then I'll talk about what's special about equilibrium smectics, why we love them so much, why people like me have been working on them for over 30 years, and Tom's been working on them for at least a year longer than that. And then the amazing thing about equilibrium smectics is that they're infinitely soft. The amazing thing about active smectics is that they're not. Okay, and this is something that Sriram Ramaswamy was the first one to figure out, and that's one of the ingredients that goes into our model, and I'll describe that. Then I'll present the hydrodynamic theory, which shows that they're not soft. And finally, I'll talk about how that hydrodynamic theory implies, among other things, that a phase like this melts via Koslitz-Thouless melting, which is quite surprising because this is a system that's way out of equilibrium. And the melting transition can be driven actually by nonlinear effects in the dynamics that would not be present in equilibrium dynamics, and yet the phase transition is in precisely this Koslitz-Thouless universality class. It's amazing but true. And hopefully I'll be able to explain all that. Okay, so first of all, what's a smectic? As I said, everybody in the audience already knows this. It's a layered system. Just to be very explicit, it's a layered system where there's no translational order along the layers, but there's translational order in the regular spacing of the layers. Okay? And that's why it's called the liquid crystal. The layers can be either one-dimensional lines in a two-dimensional system or two-dimensional planes in a three-dimensional system. The model I'm going to write down would describe both. I'm going to talk mostly about the behavior of that model in 2 dimensions. Okay? All right, so that says all that. So the interesting, okay, so how do you describe fluctuations in a smectic? What I just drew was an essentially perfect structure. All the layers were flat, they were all parallel, they were all perfectly uniformly spaced. In a real system with noise or with thermal fluctuations, there are going to be fluctuations about that. How do you describe those? Simplest description is with a displacement field U of R, which is defined in analogy with the displacement field in a crystal. So, sorry, back up. There's a perfect smectic. Here's a smectic that's, oops, going the wrong way. There's a perfect smectic. There's a smectic that's fluctuated. Okay, so the layers have moved, and now they're no longer flat, they're no longer parallel, they may no longer be uniformly spaced. And the way to characterize that is at every point R, you ask how much did the layer move from where it was in the perfect state. And that quantity is a number. It's got units of meters. It's called U of R. Okay? Now, what's special about equilibrium smectics is that they're infinitely soft. And what I mean by infinitely is, of course, a scaling statement. And the reason they're infinitely soft is the symmetries of the system. Okay? I should have specified at the outset, I'm talking about systems that spontaneously layer in a way, in a direction that is not picked out externally, but that they spontaneously pick out themselves. So they're spontaneously breaking rotation invariance as well as translation invariance. So these locusts don't have anything that tells them, you should move north. They're just trying to avoid the guys who are chasing them, and the system self-organizes to pick some particular direction to move in and some particular direction for the layers, and nothing external tells you what to do that. So the underlying dynamics are rotation invariant. Okay? That would be true no matter what phase these things went into. What's really special about a smectic is that even though you break rotation invariance and break some translation invariance, you also preserve some translation invariance. You have some liquid-like directions. And the combination of those two things makes smectics infinitely soft compared to crystals. Okay? And the way to see that is to look at one particular type of fluctuation of the smectic layers. This is called an undulation. If you want to get mathematical about it, it's a field U of R, which can be represented by a plane wave, and the plane wave has its wave vector in the plane of the smectic layers. And for such an undulation, you can ask, how does the energy of this undulation, if I consider two undulations with the same amplitude of the wave, but different wavelengths of the wave, how does the energy scale with that wavelength? Okay. In a smectic, the energy scales like 1 over that wavelength to the 4th power. And the reason you get 4 powers is that basically it's not enough to tip the layers to make this cost some energy. You have to actually bend them. And bend comes from a second derivative. And then if you make a Hooke's law model, you get the square of that. So you get 4 derivatives, hence 4 powers of length. So a long wavelength distortion like this costs extremely low energy, even lower energy than what you would be used to if you were used to thinking about phonons in a crystal. Okay? And to make that explicit, if you had an undulation like this in a crystal, now remember in a crystal you would also have vertical layers, vertical bonds running this way as well as these horizontal bonds. And if you work out the elastic theory of that, it's easy to show that the energy of an undulation like this scales like 1 over the wavelength squared. So in both cases the energy goes down as the wavelength goes down, but kind of like the brain of the penguin, if you scale it up to the size of a human being, here it goes down even faster. Okay? And in fact, if you look at the ratio of these energies, what is the energy of a particular undulation in a smectic? What's the ratio of that energy in a smectic to the corresponding energy in a crystal? You find that ratio itself is a function of wavelength, and it goes to zero in the limit of wavelength going to infinity. So it's much easier to create an undulation in a smectic than it is to create an undulation in a crystal. Okay? Another way to mathematically represent the same thing is that the Hamiltonian for a smectic has a very conventional first derivative squared term for distortions perpendicular to the layers, sorry, which just corresponds to squeezing the layers together, but it has a second derivative squared term in the energy for undulations, and this is just saying that the energy cost is proportional to the curvature of the layers squared. Okay? All right, so that's what I was told back in my infancy when I started working for David Nelson when he was trying to persuade me to work on these bizarre things called smectics. That they're interesting precisely because you have these these directions in which fluctuations are very soft. It's very easy to create fluctuations. This leads to all kinds of phenomenally cool effects which have kept people interested in smectics for probably half a century now. One of them is that the Landau-Piles instability, the fact that positional fluctuations actually diverge as a function of system size in a big system, happens not in 2 dimensions as it does in a crystal, but in smectics it happens in 3 dimensions. If you go down to 2 dimensions, the divergence is not just logarithmic as it is in crystals, but it's like a power law in 2 dimensions. So that's one of the striking phenomena that come out of this softness. By the way, the principal reason for this transparency is so that I could have my name on the same transparency as de Gennes and Landau. But anyhow, so that's one effect. A second effect, okay, so that's just a statement of the same effect. What Nelson and I also showed in this paper, by the way, I love this because this was my very first paper. I should have covered up the date, though. So what we also showed in this paper was that actually you can't even have a smectic phase in 2 dimensions, that things are actually even worse than this suggests because this ignores dislocations. And if you put in dislocations, they destroy the smectic phase altogether. So we should have called the paper No Smectic Order in 2 dimensions, but we didn't think that would sell so well. Okay. The other cool thing, and this is work that I did with Sriram Ramaswamy back when we were both slightly past our infancy, we discovered that smectics are the best soundproofing material in the universe. Okay, and let me just, all right, not going to go into that in detail, but it turns out that they are, and I'd be happy to give you as many details about that as you want. It's a very, very cool discovery. All these things arise because of the enormous thermal fluctuations you get in the undulation of the layers, because it basically costs hardly any energy to create them. Okay, so that's why equilibrium smectics are cool.
Is the sound thing just because the elasticity vanishes? I mean,
It's because the elasticity is weak, you get big fluctuations. And so if you send a sound wave, if you send an external, sorry.
yeah, but at long wavelengths it's just zero, in fact, right? I mean, you just show.
No. Oh, sorry. It's a little complicated here. You can keep the smectic layer stationary and send a sound wave through the system because you can just create a compression wave. Okay? The layers don't have to move to do that. Okay? But what happens is that you can't actually keep the layers stationary. At finite temperature, they're always going to be fluctuating around. Because of this, they're fluctuating around like mad. So if you innocently try to send a compression wave through a smectic, it's going to encounter all of these thermally excited undulation waves, and it can actually scatter off them. Now that also happens in a crystal, but in a crystal they aren't very big, and they don't do much to the ultrasonic attenuation. But in a smectic, they make contributions to the ultrasonic attenuation that, relative to the normal ultrasonic attenuation, diverge in the limit of wavelength going to 0. And in fact, there are experiments that show that the ultrasonic attenuation in smectics at acoustic frequencies are more than 1,000 times as big as they would be if you take the same material heated up out of the smectic phase. Okay? And that's coming entirely from this effect and fits bang on with what this model predicts, which basically just tells you that we understand the hydrodynamics of equilibrium smectics. Okay, so all kinds of cool things happen in equilibrium smectics. The simplest model you can write down for this, which wouldn't enable you to understand ultrasonic attenuation, but would be a simple model to give you some idea about dynamics, is just assume that the smectic layers sort of ooze downhill towards their state of lowest possible energy. Fancy way to say ooze downhill is time-dependent Ginsburg-Landau model, hereafter called TDGL. And this is just the model. You just say that the time derivative of u is proportional to the local derivative of that smectic energy that I wrote down with respect to u. And what I want to call your attention to here is that if you just looked at the z part, it looks like an ordinary diffusion equation. But if you look at the perp part, that is the part that governs fluctuations that vary in the direction of the smectic layers, those are subdiffusive. They go even more slowly than diffusion. You have 4 derivatives here instead of the 2 derivatives you would have an ordinary diffusion equation. And that means that not only is the energy cost low, but the dynamics are very slow at long wavelengths in smectics compared to what you would expect in a Gordon variety system. Okay, everything I've just told you is about equilibrium. This is all old stuff. So now the question is, what happens if you make these things active? So what's an active smectic? Well, here's a little cartoon that this is one of the first complicated figures I tried to make in PowerPoint, so it took me days. So I'm going to make you see it even if it doesn't tell you very much. Okay, so the idea is non-equal activity. To me, I had a big argument about this with somebody in Dresden a couple of weeks ago, but to me activity means alive. It really just means non-equilibrium. Okay, so what happens if you have a bunch of rods that want to form a layered structure, a smectic structure, but now they're active, they're alive in some way, they can use energy to do work. Okay? Well, one example of this is they could all carry motors. Okay? And if they're apolar, and amazingly enough, things like this occur in nature. There are cells in nature that have motors at both ends. And the motors twirl like mad, and the cells just sit there. In fact, one example of such a cell is the cells that carry melanin. At least in those of you who can get a suntan. It doesn't work for me. But anyway, so you can have apolar motors like that. That's the case that Schroer and Toppin and I worked out earlier. But what I want to talk about today is what happens when you have polar motors, when you have a more intelligent system where the motors are all pointing in the same direction. So now if you form layers and the motors all point in the same direction, the layers are going to move. Okay, the motors are going to propel the particles are going to drag the layers with them, and the system will move. It'll develop a non-zero velocity, and on symmetry grounds, there's only one direction that velocity can point, and that's perpendicular to the layers. Actually, that's not quite true, but I want to consider the case where the velocity only points perpendicular to the layers. Okay, so that's what I mean by a polar active smectic. And if you want to add one more adjective to that, this is a polar active smectic A. And if you wanted to make it more complicated, you could consider a polar active smectic P or C, where the velocity was running that way, or even what we call an active smectic P, where the velocity runs in that direction. But I'm going to focus on this case because this is the one we've done the most work on. Okay, any questions so far? You guys aren't taking advantage of your opportunity for revenge. Okay, there we go. I'm sorry?
What was that about the penguin? So
You know how if you compare the brain of a penguin to the brain of a human being, the brain of the penguin is smaller than the brain of a human being, but it's not a fair comparison because the penguin is smaller. If you scale the penguin up to the size of a human being, its brain is still smaller than a human's, but the important point is it's bigger than it was. And if you scale it, and it goes on, if you scale the penguin up to 30 feet high, it has a brain as big as a human being's and so on. Okay. It's a Monty Python sketch for the non-English people in the audience, or the English people in the audience who are less than 40 years old. Okay, so this is the system I want to consider. All right? All right, so what I want to do is I want to write down a continuum theory for this. So how do you do that? Well, one way to do it is to do the sort of thing that Tanny talked about earlier today. Start with some microscopic model, work really hard, and derive the continuum equations. I don't like to work really hard, so that's not the approach I'm going to take. Okay? In a lot of cases, you could work as hard as you wanted, and you wouldn't be able to do that. Okay? So I certainly wouldn't be able to do it. Okay, so I don't want to take that approach because it's hard. I also don't want to take that approach because it's not always clear what in the results you get is universal and what depends on the particular microscopic model you chose. I want to find the features that don't depend on the details of the microscopic model, the features that only depend on the symmetries. Okay? So this is kind of like the situation that Navier and Stokes were in 1922 when they invented fluid mechanics, right? They didn't have a theory of atoms and molecules. In fact, I don't know that they were even sure that fluids were made out of atoms and molecules, right? They didn't even know statistical physics, right? Boltzmann hadn't been born yet, much less committed suicide. They didn't have any computers, so they certainly weren't going to do some microscopic simulation, right? I'm loosening you guys up for the pub, by the way. That's really the reason I was put at this time slot. They didn't have computers, they didn't have iPads or iPods to make themselves feel better about how hard the problem was. Nonetheless, they wrote down the Navier-Stokes equations, and the reason you've heard of them is that we still use them today. That's the continuum model of fluids, and you can write it down without having any of this machinery. We want to do the analogous thing for polar smectics, okay? And sorry, back up. So we want to postulate just on symmetry grounds what the equation of motion for this field U of R and T in an active polar smectic is. So how do you do that? Well, it's the time and true method of theoretical physics. You just make it up. Okay? Now, there's a lot of equations of motion you could write down if that's all you say. Okay? So you have to impose some rules, some restrictions that limit the possible terms you can write down. So what are the rules? What are the restrictions? Well, first of all, we're doing a continuum description, so we're not looking at the scale of an individual particle. So we're restricted to looking at scales that are very large compared to an individual particle. So it doesn't make sense for us to include in our equation terms that are only important at short length scales. We should only include terms that are important at the longest length scales. If you think about it for a minute, that means we should only include the terms that involve the smallest possible number of space derivatives. If you apply the same argument in the time domain, you want to include the smallest possible number of time derivatives. Okay? That kills a huge infinity of possible terms you could put in your equation. The other thing we want to do is we want to work to the lowest necessary order in U of T. And I highlight the word necessary because you might think you could get away with a linear description. It turns out here you can't. Okay? You have to go to quadratic order, but fortunately you can stop there. And there's a way to decide how far is far enough, and we do that. Finally, and the most importantly, you have to respect the symmetries of this problem. And remember, I emphasized over and over again that this system has rotation invariance. The direction the layers form in and the direction the system then chooses to move in are spontaneously selected by the system itself. You don't impose them from outside. Okay. So if we impose all those constraints, well, first of all, if you make this sort of argument for a simple fluid, you get the Navier-Stokes equations. There's just nothing else you can get. Okay? So if it worked there, it should work for active smectics, so that's what we do. And if you think about it, you just start writing down terms that are consistent with all those symmetries and with having the smallest possible number of derivatives. This is the equation of motion you get. Okay, so this is just math. This is just, these are the terms that are allowed. Of course, once you write the equation down with 20/20 hindsight, you can go back and say, oh yeah, if I'd been smart, I could have figured out that I needed to have all these terms. So for example, V0, that's just the speed that the layers move at, right? If the system is active and it's moving, the layers are going to move at some speed. V0 is just the parameter that gives that speed. Okay? This is also a speed, right? If you only had this term in the equation of motion and you created a perturbation in the field U, it would move, and it would move at a speed that's given by 2 lambda perp. There's nothing that guarantees that the speed that a fluctuation in the layers moves at is the same as the speed that the layers themselves are moving at in the absence of a fluctuation. In fact, in the extreme case, you can imagine the layers sitting still, but if you make a bump, the bump moves up from layer to layer to layer. Okay? So that speed could be different from that speed. There's no reason either one of them should be 0, so I include them both. Okay, what else do we have? We've got these two things which look like anisotropic diffusion constants. You'd expect them to be anisotropic because parallel to the layers is different from perpendicular to the layers. You have these weird nonlinear terms, which I'll come back to. There's this weird symmetry that if you're interested, I can go into in detail, but I'm not going to do that here. And finally, there's noise. And that's important here. I'm considering a system where there's noise. You can think of that as either thermal fluctuations if you're talking about a really small system, or active fluctuations if you're talking about a big system. So for example, to give an example of active fluctuations, if these locusts are running away from their neighbors, but they aren't perfect in picking the optimal direction to run, so they make mistakes, that'll be a source of noise. Okay? So that's the model. I want to compare this with the equilibrium model and show you the freaky things that happened. Okay, so here's the equilibrium model. The most crucial difference between the equilibrium model and the non-equilibrium model is right here. Remember, in the equilibrium model, because the equilibrium model is soft, you had 4 derivatives here. In the corresponding non-equilibrium problem, you only have 2 derivatives. And this was the big insight that Sriram Ramaswamy had many years ago in a different context, and then had again in the context of the apolar active smectics, and it also applies to these polar systems. Okay? So this is what I mean when I say that active smectics are hard compared to equilibrium smectics.
John,
Yes?
if you change z to minus z, then you should also change u to minus u, no? And then the second term transforms differently than the left-hand side.
Right, but that's why it's important that this be polar. This system does not have the symmetry z goes to minus z and u goes to minus u. Thank you for pointing that out. Right. So the work that Sriram and Tappan and I did, we considered systems that did have that symmetry, and then we were not allowed to have these 2 terms. Okay. But you're still allowed to have that term. Okay. So you have this term. So this term you have even in the apolar system. These 2 terms you don't have in the apolar system. You also don't have this term in the apolar system or this term. Okay.
Equations of phase dynamics in theory of non-equilibrium patterns.
Yeah. Yeah, exactly. No, this would also apply to that, absolutely.
John,
Yes.
when you said that the elasticity was so weak, I thought that I would have gotten at some point some nonlinear equations in the strain field.
You mean here in the equilibrium case? Yeah, the real equation would be nonlinear. I don't want to get into the nonlinear terms down here because they're different than the nonlinear terms that are important up here. But yeah, there are nonlinear terms in that, absolutely.
Which would be overwhelmingly important as you make the thing softer and softer. That would be very important when you make the thing softer.
Yes, and in fact, it's those nonlinear terms that gives rise to, among other things, the exceptional soundproofing properties, right? To have a compression wave interact with these undulations, you need a nonlinearity. Absolutely. Yeah, that's true. Yes?
Is there any relationship between the lambda pair and D0?
No. That's the surprising but true thing. The speed that the layers move at does not have to be the same as the speed at which a pattern in the layers moves at. They're completely independent. Okay. Now, if you really wanted to embarrass me, you could ask me, can you derive those 2 parameters from a microscopic model and show that they're different? And of course, the answer is no. But somebody like Kenny probably could. I don't know if he's going to do it, but
Can you say again why you got the new term? Did you?
yeah, I'm about to make a song and dance about that. Yeah, because this, I should say, by the way, that when Sriram first pointed out the existence of this term to me more than 10 years ago in a different context, I told him that he was absolutely wrong. That we all know that in Smectics, this direction has to be soft. And he expended a lot of time and effort explaining to me why that was actually true. And now I'm going to give you, hopefully not too mangled a version of the argument he gave me. Yes?
Equilibrium equations, equilibrium terms are presumably still there, you're just saying they're subbed out.
Yeah, oh, absolutely, right.
The interesting thing is the 4th and 2nd derivative can give you an intermediate length scale in principle, which isn't microscopic.
That's right. If they aren't competing with each other,
Yeah.
that is, if they're both in the direction of stability, that length scale turns out not to be terribly important. But you're right, yes, absolutely. And in fact, you could get into questions about the interesting crossover between equilibrium behavior and non-equilibrium behavior if you had a system that was only weakly active. And that's something that would be on my to-do list if I hadn't given up making to-do lists 20 years ago. Yeah.
So now I'm confused about the words are going with V naught. In an equilibrium system where the velocity of the particles is added, you would have a V on the right-hand side at the bottom of the
You mean if the
keep track the momentum of the particles as well as the
yeah. Sorry, Tom. I should have said this is the equation of motion for a smectic that's sitting on a substrate, so there's no momentum conservation.
But when you start saying the pattern doesn't have to move at the same rate as the periodicity,
Mm-hmm.
then in the case of the bottom, you would have to have a V naught also, which is just the momentum of the particles.
No, but I'm saying we're considering a system that is in contact with the substrate, and we're in the reference frame of that substrate, and so it's not going to move.
If I do that, you can add the V naught at the top of it.
Yes, because these are active, right? So the idea is you have locusts, and they're on the floor, and they're alive, right? They have feet, so they can actually push on the floor, and they actually generate a non-zero value of this. If you kill them, that goes away.
So, John,
Yeah.
you can always go into the frame where you get rid of that V naught, just like you do.
Yeah, no, and in fact, when Leming and I do our analysis, this is the very first thing we do. I'm just trying to be complete here. Yeah. I should say this whole discussion is about terms that you can shift away by doing coordinate transformations. So the important these first two terms don't really matter much. The important terms are everything else. Okay? Any other questions? Seriously, I love this. So the more questions, if people have more questions, please ask them.
You have 3 minutes left.
Don't mess with my head, Tom. Remember, I'm not using a laser pointer. Okay. All right. So why is this? What is it about an active system that makes it possible to get this, whereas in an equilibrium system you can only get that? Okay. Well, there's two answers to that. Never mind the noise. Oh, all right. The noise is a Langevin white noise, just in case you're wondering. Oh, yeah. No, I should say one thing about this. So the noise is a Langevin white noise, so the only important parameter is its variance. We call that variance delta. Delta acts like a temperature in this problem. If delta is bigger, you have more noise. It's creating more fluctuations. And so you might expect that if you turn delta up enough, you could actually melt the smectic. And in fact, you can, and that's the transition I'm going to talk about towards the end. Okay. So why do you have this weird term? Why is the active smectic not soft? Well, there's two answers, and the first one is sort of technical, but it's the most compelling. The second one is sort of physical, and it makes you feel like you understand it. So first, here's the symmetry argument. Okay? So let's just look at the terms, the biggest difference between the two equations. Why is this 2 derivatives and this 4 derivatives? Okay? Well, your first thought might be it has something to do with rotation invariance, but both models are rotation invariant. And if you think about it for a minute, you can easily convince yourself that this model and this model are both rotation invariant. If you create a U that varies only in that direction, that corresponds to tipping the layers a little bit. That means U is linear in X. If you put in a U that's linear in X on the right-hand side of either one of these equations, you get 0. So both equations are rotation invariant. Okay? So that's not the difference. The difference is that the one on top is active and the one on the bottom is not. And what does that mean? Well, if a system's not active, you have to be able to derive the equation of motion from an underlying Hamiltonian. And that underlying Hamiltonian has the same symmetry constraints as the equation of motion. So this has to be derivable from a Hamiltonian that's rotation invariant. And the only Hamiltonian we can write down that's rotation invariant was this weird one that involved second derivative squared in the perp direction. Okay? All right, so here's that just said mathematically. This has to be the derivative of a Hamiltonian, and that Hamiltonian has to also be rotation invariant. But the top equation is not a system out of equilibrium. So you do not have to be able to write this way. And if you do cleverly figure out a way to write this way, there's nothing that tells you that the thing that goes up there has to be rotation invariant. The only constraint is that this equation of motion at the end be rotation invariant. Okay? And that's the difference between active and equilibrium systems. And so on that basis, because the top equation is rotation invariant, this term is allowed. Okay, so that's the symmetry argument, and that's the argument you make to the referee to shut him up. It doesn't give you any physical insight into why that term appears, so let me try to give you some of that. Okay, and this argument, I should say, is also due to Shriram. So suppose you have an active smectic, and now you create a curvature. That curvature creates a non-zero value of del perp squared u. Okay? Now suppose this is an equilibrium system. In an equilibrium system, if you're this molecule here, you look to your left, you see a molecule tip to your left. You look to your right, you see a molecule tip to your right. You'd like to point in the same direction as both of them, so what do? You point in the average direction, which is the same direction you're already pointing. So you don't move. And that's true for every molecule everywhere along this layer, every molecule along this layer. So distortion like that will just sit there in an equilibrium smectic. And that's because if you work it out, the fourth derivative term vanishes here. Okay? You've actually got to, it's not enough to have a curved layer to create motion in an equilibrium system. You have to have a spatial variation in the curvature. Okay? Now what about non-equilibrium? Well, non-equilibrium, these guys have little motors on them. Okay? So imagine these guys have little propellers at the back. Okay? When they were parallel, the propellers were nicely out of the way, and so they could all scoot along very merrily. But now, the backs of them, the ends, are pressed closer together. So presumably they get in each other's way and they slow down, so this bent layer isn't going to move up quite as fast as the flat layers on either side of it. Imagine this is a bump in a system that's otherwise flat, so the flat layers on the other side will move faster than it, they'll catch up, and they'll smooth this out. And if you work it out, you'll find that that gives rise to a velocity that's proportional to the curvature, and that's exactly our new perp term. Yeah?
Does this not depend on the boundary condition of a frame which is holding the layer? I mean, just think about one membrane sheet. You don't really need this. So in equilibrium, we know that if the membrane is supported by a frame, then the surface tension could be non-zero, will be non-zero.
Right, but in a Smectic, if you assume the system can organize itself to make the layer spacing be what it wants, then it will automatically adjust itself to make the tension zero. It's like if you take a lyotropic Smectic, okay, a single soap film has a surface tension. But if you put a finite concentration of soap in water, first you'll get one layer, then you'll get a second layer, then you'll get a third layer. It'll keep pulling soap into the system until you get a layer spacing that's such that the surface tension is exactly zero. And that's why in a lyotropic Smectic you don't get a surface tension-like term. You don't get a term like this. The system automatically tunes itself to have zero tension. Okay? It's different than a situation where you just have one layer. Provided you allow the system to make more layers if it wants to. Okay? So this argument ultimately gets into questions about whether you allow dislocations to form and move the layers into the system or not.
Maybe we can discuss it later.
Yeah, it is complicated.
Even if you have exchange with the bulk, you can get a membrane tension depending on whether you have a frame or not.
Right, but you cannot in a system where you have many layers and you can adjust the number of layers. Okay. All right. So that's physically where this effect comes from. It's just if you have motors, their functioning can be affected by local curvatures, and that's all this says. Okay. Now I want to make some connections to other problems because it's a lot easier to solve things if you map them onto things that other people have already solved. And so that's what I'm going to do. There's two connections we can make here. One is that the equation of motion that I wrote down for active Smectics looks just like a purely relaxational model, a time-dependent Ginsburg-Landau model, for an equilibrium XY model. So that's the XY model is just a model where you have arrows pointing in a plane, and you say that they all want to point in the same direction, so there's an energy cost for making them point in different directions. That energy is proportional to the square of the gradient of the angle that they're pointing at. Okay? So that's the XY model. And if you just write down simple oozing dynamics, time-dependent Ginsburg-Landau dynamics, you get a simple diffusion equation. Okay? And that looks a lot like our equation of motion. If you can actually do the thing that several people have already been urging me to do. You can change coordinates to get rid of these first two terms, and then you can anisotropically rescale lengths to make those two coefficients equal, and when you're done doing all of that, you'll get an equation that's got exactly the same form as the equation for the 2D XY model. So this active Smectic dynamically looks like a two-dimensional XY model. Okay? And I'm going to use that analogy later to treat dislocations in these active Smectic patterns. Okay. The other connection is that, I should say one thing. This analogy only works if I linearize the equation of motion. Okay, you'll notice that if you compare this equation to the one I showed a couple of transparencies ago, I've dropped the two nonlinear terms, okay, which turn out to be important. Okay, so I'm going to have to go back and figure out the effect of those nonlinear terms. Turns out I don't have to do any work to do that either, because somebody else has also worked that out. It turns out that the equation I wrote down is something known as the anisotropic KPZ equation, named after its three inventors, its four inventors, Cordar, Parisi, Zhang, and anisotropic. And so this is a model for a growing surface. So imagine you have a surface like this, and I deliberately took a nice symmetrical surface and stretched the image to make it anisotropic. Now imagine you're dropping atoms on this from above, so this surface is growing. And you try to write down a dynamical equation for the evolution of that surface. Well, it was done, and it looks exactly like the equation of motion we wrote down for an active Smectic. Now the height variable is no longer the position of a bunch of layers, it's just the height of this surface above some reference plane. Okay. So it looks like our problem has already been solved. It looks like I've turned our problem into the anisotropic KPZ equation, but that's actually not true, because there's one crucial difference here, and that difference has to do with dislocations. Yeah? Mm-hmm.
What's the interpretation of the maxima, minima, and saddle points in the height of the anisotropic KPZ when translated in the language of your fluid? Like, is there a mapping between the singularity of the fluid and the extrema of the height field?
No, it's a question I don't quite understand. The height field is analogous to the displacement field. I think I'm missing the point of your question, and if I try to get the point of your question, I'm probably going to run out of time. So could we perhaps defer this afterwards? Sorry, it's my fault. I'm being stupid. Sorry. Okay. There's a crucial difference between this surface model and the Smectic model, which is the Smectics have dislocations and surfaces don't. Let me just remind you, there's a picture of an active Smectic, and the dislocations are the places where the layers end. Okay. Now, again, I'm bringing coals to Newcastle here for most people, but let me just remind you what a dislocation is. Okay, it's a place where a Smectic layer ends, and there's this great thing called the Berger's construction, which enables you to figure out, without actually seeing the whole picture, whether you've got a dislocation there or not. What you do is you just go for a walk around the dislocation, and if you take an equal number of steps up across layers and down across layers, but find yourself not back where you started, you know there had to be a dislocation in the middle. There had to be an extra layer stuck in on one side. Okay? The other thing you notice, the thing I want to call your attention to about this construction is it says that if you introduce a dislocation, you no longer have a single valued U field. Right? Here, I said this layer was at U equals 0. I walked through a bunch of layers that were uniformly spaced, so I would call that point still U equals 0. Then I walked over here, the layer had to slope up because this extra layer shifted in. And if you go for this walk, you'll find out that if you define U to be 0 up here, when you get to a point just below the point you started, you now have U equals A, where A is the spacing between the layers. Okay? So the U field is no longer single valued, or if you want to make it single valued, you have to introduce a cut where it jumps discontinuously from A to 0. Now in a Smectic, there's no problem doing that, because if you take a picture of a Smectic and shift it up by exactly one lattice constant, it looks exactly the same. But try doing that to a surface. You'll find you tear it. Okay? The cut becomes a real cut in the surface. Okay? So this is what happens if you try to make a dislocation in a surface, like the surface in the anisotropic KPZ equation. Clearly, things like that are not going to happen. But in a Smectic, dislocations certainly do happen. And that's the big difference. Okay? So that's what makes what we're doing go beyond just quoting the results of the anisotropic KPZ equation. Okay. The important thing is we know from equilibrium physics that dislocations can unbind and destroy order. In this case, it's the Smectic order. And this turns out to be a Kosterlitz-Thallis melting in this active Smectic case. I haven't shown you that yet, but it's true. Okay. So how do we figure out what happens if we put all this stuff together? The nonlinearities in the AKPZ equation and dislocations. Okay? Well, the way you answer it is you do something called the renormalization group. The idea of the renormalization group is you just take the initial stochastic partial differential equation you have, average out the short wavelength fluctuations, and get a new equation for the long wavelength fluctuations. The symmetry of that new equation has to be the same as the symmetry of the old equation, so it has exactly the same form, but the parameters in that equation, which I remind you, the important ones are the noise strength delta, these two diffusion coefficients, and the two nonlinear coefficients, those will be different in the V-scaled equation. Then you just keep repeating this process and you see what happens to these parameters. Okay? If you're lucky, these parameters flow into a regime where the problem becomes simple. Those are all the problems that we know how to solve. Unfortunately, this turns out to be one of them. Okay, so what happens if you do this? Well, if you ignore dislocations, it's great because you don't even have to do it. Somebody else already did it. This guy Wolf did it back in 1991 in the context of an anisotropic surface. So we can just copy his results. Okay? It turns out we couldn't quite copy all his results because he didn't do the calculations we really needed to do. But what I'm going to show you is a picture of the flows in these two parameters. These are combinations of the parameters in the equations of motion. All you need to know about them is that this parameter G tells you how important the nonlinear terms are. And this parameter gamma tells you how anisotropic the system is. Okay?
G also tells you about the noise.
I'm sorry?
G also tells you about the noise.
Yes. Yeah, I should have said that. So the only reason the nonlinear terms are important at all is that there's noise. Right? If there was no noise, you could always say, I'm going to deliberately only perturb my system a little bit. But if there's noise, you don't have that choice because the system is spontaneously perturbing itself by some amount that may be too big for linear theory to work. Okay? So that's why the noise comes into this. The diffusion constants come in because they suppress the fluctuations. Okay? So these are the two parameters. It turns out you can write the RG equations for all those parameters. You can combine them into flow equations for these two parameters. And this is what they look like. Okay, so here's the anisotropy parameter. Positive anisotropy means the two nonlinear terms have the same coefficient, the same sign of the coefficient. Negative anisotropy means they have opposite signs. Okay? If they have the same sign, what happens is that initially, if you have a small enough anisotropy, the nonlinearities become less important for a while, but then they turn around and become more important. At the same time, the anisotropy goes away. Okay? Ultimately, this runs away to infinity, the nonlinear terms become important, and the problem becomes hopeless. Okay? What we think happens over there is that well, in the context of a surface, that becomes a rough phase. The nonlinearities actually make the surface very rough. If the anisotropy is negative, it turns out the flows always come down. And eventually, the nonlinearities become unimportant. You can do a linear theory over here. Oddly enough, the anisotropy remains, but it now becomes exactly -1 instead of +1. Freaky, but 2. OK, so here you can use a linear theory, and the linear theory predicts that the surface should be smooth. By smooth, I mean it's only logarithmically rough.
Is this a momentum shell RG or?
Yeah, momentum shell. In fact, it's a freaky square Brillouin zone and all kinds of bizarre stuff. But fortunately, we didn't have to do it. So it was OK. We just had to analyze it. OK, so that's what the flows look like in the anisotropic KPZ equation. For the active polar smectic, the way we interpret this is if you're over here and the nonlinearities become important, they actually drive the proliferation of dislocations. And so over here, you're not in the smectic. You're actually in a different phase called the active pneumatic, which people have talked about today. But over here, you have at least a chance to get into the active smectic. Now, it turns out it's a little subtler than that because of the dislocations. But this is the side where you have a chance to have an active smectic. Over here, you're dead. There's no chance. OK, so how do we include dislocations? Well, what we do is we consider the low fugacity limit, which is a fancy way of saying we're going to put dislocations in, but we're going to insist that they have a very low density. Okay? Now, you may think that's a bit of a cheat, but it's the same cheat that everybody else does going all the way back to Kosterlitz-Thalès. It's all we know how to do. Okay? So we'll assume the dislocation density is low. So now I just want to introduce some notation. I can't keep drawing all these layers. It takes too much time. So I'm going to use this little symbol to mean a dislocation where the extra layer comes in from the left, and a fairly obvious related symbol to mean a dislocation coming in from the right. Okay? So here's a picture. No layers are shown, just the dislocations are shown. So now suppose you start running an RG on this. The RG means averaging over short wavelength degrees of freedom. So you start out by averaging over degrees of freedom in a box that small. Then you look at a box that's that big. Then you look at a box that's that big. And you'll notice I cleverly placed all 3 boxes so that none of them contain the dislocation. Now, you don't have to be clever if the density of dislocations is low enough. You're almost guaranteed to achieve that until the boxes get too big. So what I'm assuming is that we're looking at a system where out to some very long length scale, that is, out to running the normalization group for some very long time, we never encounter dislocations. In that case, we can use the results I just quoted. So what we're going to do is we're going to use the results I just quoted, hope we flow into a regime where the problem becomes linear. When the problem becomes linear, oops. I showed you earlier, it becomes an XY model. So now I can just quote some other results, namely the results for the equilibrium XY model. Okay? So that's what I do. And this is a perfectly sound argument as long as the dislocation density is low. Okay? Among other things, the critical density is determined by the strength of the nonlinearities. So, yeah. OK, so the effective equation becomes linear. You can just quote results from Kosterlitz and Thalès. So the big question is, when you follow those anisotropic KPZ flows, do you get down to the linear regime before you start seeing dislocations or not? If you do, then you can use the linear theory to decide whether the dislocations are bound or not. If you don't, they're probably unbound. Okay? So if you make that argument, you can get a phase diagram. And here's the phase diagram. I've slightly changed the axes on you. The horizontal axis is the same. It's the anisotropy. The vertical axis is now the effective dislocation temperature, and the nonlinearities are gone. Okay? And this is what the phase diagram looks like. It has a peculiar V-entrant structure. So this is a really weird thing. If you start with something where the anisotropy is near 0, so one of the nonlinear coefficients is near 0 and the other one is non-zero, and they have opposite signs, you'll be in a disordered phase. There'll be no Smectic order. If you then increase the nonlinear coefficient, decrease the nonlinear coefficient that was initially small, that is, make its magnitude bigger, make it more negative, you go into the Smectic phase. If you keep going in that direction, you come out again. There's a weird sort of re-entrance. Strange but true. The embarrassing thing is I don't know how to tell somebody who's doing a simulation how to move along that exact path in this phase diagram. If you tweak something in the simulation, you move along some arbitrary path, and it's not clear that you'll get that re-entrance. But this is what you get. And the other thing we can conclude, because of the analogy with the equilibrium XY model, is what the universality class of this melting transition is. It's the universality class of the XY model. So here's a nonlinear, non-equilibrium system that nonetheless has a very familiar equilibrium phase transition, namely the Costa-Thalers transition. You can make a similar argument in 3 dimensions. We haven't worked out the phase diagram there yet, but you can argue that the 3-dimensional transition is the phase transition of the 3-dimensional XY model by the same sort of argument. Okay, so to summarize, equilibrium smectics are soft and have big fluctuations. Active smectics, you can analyze them using these hydrodynamic ideas, even though they're way out of equilibrium. They have smaller fluctuations, but they're still interesting. And they have this weird Costa-Thalers transition in a system that's so far out of equilibrium and so nonlinear, you never would have guessed it. So I find this quite amazing, and I thank you for your attention.
So we are, I gave John 8 minutes more than him. I think maybe, are there any pressing questions? This is by way of, what do they call exercising leadership or something? I think we've had so many questions, and we're supposed to leave in 2 minutes on our trip. Let's